Hello and welcome to today's lesson on nuclear equations, which is part of the atomic structure topic in GCSE Separate Science physics. So in today's lesson we're going to look at writing out the correct nuclear equations for the different decay processes. So if we've been successful and learnt in today's lesson, we should be able to detail the properties of the different nuclear decays, describe what occurs in each nuclear decay, and finally write out a full nuclear equation for a nuclear decay, which links into the following part of the GCSE Separate Science Physics Specification 4.4.2.2 Nuclear Equations. Now in mathematics we can represent a change by an equation. So we can say 2 plus 2 plus 2 equals 6. And in chemistry we can represent a change by an equation. So 2Na plus Cl2 goes to 2NaCl. Now an arrow is used in chemistry to denote the passage of time for this to occur. And in theory there's no passage of time in mathematics, it's a pure subject, so you can use an equal sign. So if there's no passage of time, we use an equal sign to represent a change, and if there is a passage of time, we represent an arrow sign to represent change. Now it's important to note that in chemistry we balance equations as the total number of atoms on either side before and after must be conserved. Now that's important because the word conserved means to stay the same. So in chemistry we balance equations as the total number of atoms must be the same before the reaction as afterwards. Now in physics we can also use equations to show change, and in this case the radioactive decay process, and we call this type of equation a nuclear equation, and we can do this for either alpha, beta or gamma decay. Now in physics we've got to be aware that the number of protons and neutrons are conserved in nuclear decays. So in physics we've got to be aware that the number of protons and neutrons are the same before a nuclear decay as after a nuclear decay. So it's a very important idea that the mass number and the atomic number is the same before a nuclear decay as after. So in a question you must be able to complete decays for alpha, beta and gamma. Now you've got to recognize as well if a decay is showing you alpha decay, beta decay or gamma decay. So for example we can look at before an equation and we can look at after an equation and work out whether it's alpha, beta or gamma. Now this is not a chemical equation because it only concerns the nuclei of the atom, not the entire atom. Now this is a nuclear equation as only nuclei decay. So just remember what we've talked about before. You can represent in the nucleus of the atom A as the atomic mass, which is the number of protons and neutrons, Z which is the atomic number, the number of protons, and X is the chemical symbol as shown on the periodic table. Now in any nuclear decay the total atomic mass before has to equal the total atomic mass afterwards, which in this case is 28 before and it's 28 afterwards because it's 0 plus 28 afterwards. And as well as that, in a nuclear decay equation the total atomic number before has to equal the total atomic number after. In this case it's 15 before and it's 15 afterwards because 14 plus 1 equals 15. Now it's important to note that atomic mass and atomic number have to be conserved, as if they would not conserved, mass would not be conserved. And it's important to note that mass is always conserved in a nuclear decay. The number of protons and neutrons is always conserved in a nuclear decay, which is a key fundamental idea of both chemistry and of physics. Now we've got to be able to write a nuclear equation for each radioactive emission. So let's consider alpha decay. In alpha decay, 2 protons and 2 neutrons are lost from a nucleus when it emits an alpha particle. So alpha decay causes a nucleus to lose 2 protons and 2 neutrons, and that will increase its stability. So it causes the atomic mass number to decrease by 4 because the atomic mass is the protons and the neutrons, but it causes the atomic number to decrease by 2 as that's just the number of protons. So this means that the nucleus after the decay has occurred has changed its element because it has a different number of protons. Now the process of a nucleus change an element due to a decay is called transmutation. So because alpha causes the nucleus to lose 2 protons and 2 neutrons, it is an example of transmutation. Now alpha particles can be represented as either with the following symbols, either alpha 42 or He 42. Now it's important why this is the case because alpha particles are just helium nuclei. Now alpha decay causes both the mass of the nucleus and the charge of the nucleus nucleus to decrease. Now it's important to note that an alpha particle can be considered a helium nucleus, and each alpha particle is emitted with exactly the same kinetic energy. So 2 protons and 2 neutrons are lost from a nucleus when it emits an alpha particle. This means its atomic mass decreases by 4 and its atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table than the original element. So you can see here radon has had its atomic mass number decreased by 4 and its atomic number decreased by 2, so it forms polonium. So the atomic number has gone down by 2. So this produces a new element as there's a different proton number in the nucleus. So alpha decay causes both the mass and the charge of the nucleus to decrease. So as we said before, a new element is formed 2 places lower in the periodic table than the original element. Now in beta decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus whilst the electron leaves the atom with high energy as what we call a beta particle, and this increases nuclear stability. So beta decay causes the nucleus to turn one neutron into a proton and an electron. The proton stays in the nucleus and the electron is fired out the nucleus at a very high speed. So this causes the atomic mass to stay the same, because that's the number of protons and neutrons, and a neutron has turned into a proton. So the overall numbers of neutrons and protons has stayed the same, but it has caused the atomic number, the number of protons, to increase by 1 as the proton number's gone up by 1. This happens so we can conserve these numbers. So this means the nucleus after the decay has changed element as has a different number of protons. It's increased its proton number by 1. So beta decay is another example of transmutation. Now beta particles can be represented as either beta as in 0 minus 1 or E minus 0 minus 1. Now beta decay does not cause the mass of the nucleus to change as a neutron turns into a proton and they have the same mass, but it does cause the charge of the nucleus to increase because we've gone from a neutral neutron to a positive proton. Now it's interesting to note that a neutron wishes to turn into a proton as protons are slightly smaller, so exist with less energy. The universe tends for objects with less energy, so an energy would spread out, and a neutron will do this by changing its what we call quark structure. So in beta decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus whilst the electron leaves the atom with high energy as a beta particle. Now the nucleus has 1 more proton and 1 less neutron when it emits a beta particle, so the atomic mass stays the same, the atomic number increases by 1, so a new element is formed that is 1 place higher in the periodic table than the original element. So our atomic number has increased by 1, and beta decay does not cause the mass of the nucleus to change, but it does cause the charge of the nucleus to increase. So a new element has been formed as the proton number has changed, it's gone up by 1, but as we said before, it does not cause the mass of the nucleus to change, but it does cause the charge of the nucleus to change. Now, in gamma decay, there is no change in the makeup of the nucleus, it just loses energy. So gamma decay causes the nucleus to release only energy. So the atomic mass is remaining unchanged, the atomic number remains unchanged. This means the nucleus does not change element after nuclear decay. So gamma decay is not an example of transmutation. Gamma decay is the relaxation of a nucleus as the protons and neutrons change the way they're arranged in the nucleus. Now we can represent gamma rays with the following equation as gamma 0, 0. Now the emission of a gamma ray does not cause the mass or the charge of the nucleus to change. So in gamma decay there is no change in the makeup of the particles. It just means the nucleus loses energy. So the atomic mass number and the atomic number have not changed in this decay. Now we can denote the change from unstable to stable in gamma decay with a star or an M. Now if it's starred, it means the nucleus has to wait a short time for losing energy via gamma decay. If it's M, the nucleus waits a long time before losing energy via gamma decay. If it has to wait a long time to do this, we say it's in a metastable state. Now in gamma decay, the element of the nucleus is unchanged because the proton number of your nucleus is unchanged. So the emission of a gamma ray does not cause the mass or the charge of the nucleus to change. So nuclear equations are used to represent radioactive decay. In a nuclear equation, alpha can be represented with the symbol 4,2 helium, and the beta particle is represented by the symbol 0 minus 1 E. Now the emission of different types of nuclear radiation may cause a change in mass and or charge of the nucleus. So alpha decay causes the mass and charge of a nucleus to decrease, but beta decay does not cause the mass of the nucleus to change, but does cause the charge of the nucleus to increase. You should be able to use the names and symbols of common nuclei and particles to write balanced equations that shows alpha and beta decay, which is limited to balancing the atomic numbers and the mass numbers. Now you don't have to identify what the daughter elements from these decays are called. However, you must know the emission of a gamma ray does not cause the mass or the charge of the nucleus to change. So I hope you've enjoyed today's lesson on nuclear equations, which is part of the atomic structure topic in GCSE Separate Science Physics. Thank you very much for listening and have a lovely day.